Hello everyone, my name is Kaneesha Gandhi and today we will be talking about dynamic load balancing in parallel computing systems. Moving forward with the introduction, as we know, in recent times parallel distributed systems are beginning to replace traditional mainframe computers for huge database and transaction processing tasks. Way back in the past, the future of these parallel systems seemed so uncertain and dull even to the greatest scientists. However, with time, it has proved to be the leading solution in today's industry markets. Over the last decade, many leading companies have come up with highly powerful multiprocessing systems. Parallel computations rely heavily on data partitioning and load balancing. Many different partitioning strategies have been developed, all of which have proven to be highly effective in parallel applications. However, the load balancing problem is not completely solved. New applications and architectures necessitate new partitioning features. New models are required for non-square, non-symmetric, and highly connected systems arising from biological, circuit, and material simulation applications. Load balancing at various levels is required, particularly when assigning transactions, queries, and subqueries to nodes. Usage of super servers for database processing poses a ton of implementation challenges that are resolved by parallel systems. A major problem that occurs in efficient use of intra-query parallelism in multi-user mode is when a lot of queries are executed simultaneously with various complicated queries and OLTP transactions. There might be various parallel query processing algorithms designed for multi-user mode, but their performance would be substantially lower than single-user mode. So this paper focuses on providing a brief review of dynamic load balancing in parallel systems. The following is how the rest of the paper is structured. A background of architecture of parallel database systems is presented. Moving on, we have the parallel database application techniques, followed by the challenges in load balancing, and then lastly we have the workload allocation in parallel systems, followed by the conclusion. Architecture. There are various levels of architecture, starting with the input-output and processing parallelism. Parallel database systems are built around multiple standard microprocessors and linked together via a local high-speed network. Effective inter- and intra-transaction parallelism support necessitates the use of both input-output and processing parallelism. Input-output parallelism requires that the database should be distributed across data blocks, which is known as declustering, within or conventional disk farms or disk arrays. Declustering facilitates intra-query concurrency by reading and writing massive quantities of data analyzed by a single request from or to disk drives in parallel. Here we see the image of parallel processing parallelism, where the memory is shared with different processors at the same time. Next, we have the shared nothing, shared everything, and shared disk architecture level. Shared everything is the usage of multiprocessor systems for database processing. We have an intricately intertwined system in this case, with all processors having a common memory resource as well as external devices such as terminals and disks. To use all processors, there is only one duplicate of the DBMS code that could be executed in multiple processors. This method is also known as symmetric multiprocessing. Shared nothing systems are made up of multiple independent processing elements, each with its own private memory and running its own copy of the computer system. Message passing is used for inter-process communication. The database is divided among many of the PEs, and each database instance can only access data from specific partition directly. Non-local data access necessitates a dispersed query and transaction execution. Shared disk systems are made up of numerous loosely connected PE. To ensure every database instance has immediate access to every data object, the database is not divided but rather shared among different parallel instances. This presupposes every node has access to every disk. In this, we see the image of shared nothing, shared disk, and shared everything systems. So as we can see the differences between all the three systems, it is very evident that shared everything systems benefit from shared memory, which facilitates effective synchronization and collaboration between DBMS operations. Additionally, the operating system, which immediately assigns the following ready task or subquery to falling free CPU, supports efficient load balancing. These benefits are particularly useful for parallel query processing, which necessitates more interaction and load balancing to initiate, complete, and manage numerous subqueries. Large intermediate results can also be efficiently sent across subqueries. Dynamic load balancing for simultaneous query optimization in shared everything systems was the subject of several studies. On the other hand, there are substantial availability issues because there is only one copy of software system like the file system or DBMS, and because shared memory limits failure isolation across processors. As a result, there are only about 30 processors in current shared everything systems. Because of these issues, shared nothing and shared disk are typically thought to be more suitable to satisfy high performance and high availability needs. Hardware-wise, shared nothing systems seem to be particularly appealing. They assign each disk to a certain PE and connect all PE through a local network that is doable with affordable and conventional hardware. Furthermore, because there are no common resources, a huge number of PE can be connected in this manner. On the contrary, shared disk systems demand that all PE and disk devices be connected. All input-output queries must pass through this network, necessitating the development of multi-stage, incredibly rapid interconnection network that may be significantly more costly than the system of SN systems. Additionally, the possibility of bottlenecks within network and disk subsystem may be raised for shared disk. On the contrary, it does not seem likely that increased transmission requirements will cause a significant issue with present fiber optic connection technology. Next, we move on to the different techniques for parallel database applications. Under this, we first have the speed up and scale up. Speed up expands the system while maintaining a consistent problem size. Scale up evaluates a system's and problem's capacity to expand. The capability of an n times complex network to complete an n times larger task in the same amount of time as previous system is known as scale up. Path scale-up and transactional scale-up are two separate scale-up types. The scale-up entails y as many clients sending n times as many queries against such n times larger datasets if the job entails processing several independent small requests submitted by numerous clients and working on a common database. This scale-up is the one frequently seen in time-sharing and transaction processing systems. The Transaction Processing Performance Council uses this type of scale-up to scale up their transaction processing benchmarks. As a result, it is known as transaction scale-up. Because each operation is usually a simple individual task that can be operated on a separate processor, transaction scale-up is well suited for input-output parallel systems. When the scale-up job is introduced as a single massive job, a second type of scale-up, known as path scale-up, occurs. This is characteristic of database queries as well as scientific simulations. Scaling up in these cases entails using an n times bigger machine to fix an n times greater issue. Next, we have the hardware architecture. The ideal database device would consist of a single endlessly fast processor, infinite memory, and infinite bandwidth, all while being infinitely cheap. It would not be necessary for performance improvement, scale-up, or parallelism with such a machine. Unfortunately, innovation is not yet capable of producing such machines, but it is getting close. Fast one-chip devices, solid high disks, and high conductivity RAM are all on the way. It also guarantees that every one of those machines will be very cheap by today's standards, expected to cost only a few $100s each. The hardware architecture for parallel systems is shown below. So this is the hardware architecture that I spoke about in the previous slide. And we can see that the different shared memory consisting of various CPU systems running in parallel share a common pool of resources, that is the disks in this case. By limiting resource sharing, shared nothing architectures reduce interference. They also make use of commodity processing units and memory units without the need of a truly powerful interconnection network. The shared nothing design only allows questions and answers to travel through the network. Raw memory and disk ports are done locally in a processing unit, and only screen data is sent to software application. By reducing traffic on the network interface, this allows for more scalable design. On complex relational queries and online transaction processing workloads, these shared nothing architectures accomplish near linear speedups and scale-ups. On these database applications, shared memory and common systems don't really scale well. Interference is a significant issue for shared memory multiprocessors. To update some data, a process must first procure the most copy of that information. The next method that we have is the data flow method to SQL. As the cost of online storage falls, terabyte online databases with billions of records are becoming more and more common. The SQL relational model is frequently used to represent and manipulate these databases. An unexpected advantage of relational paradigm is parallelism. Relational searches provide many chances of parallelism because they are actually just relational functions done on very large data sets. The queries give a great deal of flexibility in terms of how they are executed because they are presented in a non-procedural language. A data flow graph can be used to represent relational queries. These graphs have the ability to leverage both parallelizing concurrency and partition parallelism, as was first mentioned in the first portion of this paper. Two operators can run in parallel and gain a potential computational efficiency of 2 if one operator passes its output to the other. Pipeline parallelism has little advantages for the following three reasons. Chains longer than 10 usually are unusual for relational pipelines, which are rarely extremely long. Second, a few relational operators delay emitting their first output till they've used up all their inputs. This property belongs to aggregate and SUN operators. Pipelining these operators is not possible. Third, a lot of time, one operator's execution cost is significantly higher than all others. The speedup provided by pipelining in such circumstances will be very constrained. Execution that is partitioned provides significantly higher prospects for speedup and scale. Divide and conquer can be used to break up a huge task into several smaller independent ones by taking the major regular expressions and dividing their inputs and outputs. Scaling up and speeding up are both ideal in this circumstance. The secret to partition execution is partitioned data. Now let's move on to the major challenges in load balancing that we see today. Parallel calculations require both load balancing and data partitioning, which are crucial elements. Numerous partitioning techniques have been created and they perform incredibly well in parallel applications. Although the load balancing issue has been somewhat resolved, new applications and architectural design call for new partitioning features remains surge even today. To enable increasingly complicated applications, existing algorithms must be improved. For non-square, non-symmetric, and densely connected systems originating from simultaneous of biological systems, electric circuits, and materials, new models are required. Partitioners that take into account non-uniform compute, network, and storage resources are needed due to the growing use of diverse computing systems. And in order to have the biggest impact, these new tools need to be provided in toolkits that are strong, simple to use, and suitable for a variety of applications. In parallel simulations, task scheduling grouping of work to process units is very critical. It improves application performance by minimizing processor slow time and interprocessor communication. Load capacity balancing may be employed as a preprocessor in use with constant workloads. Other implementations like responsive finite element analysis have unpredictable or changing workloads. These programs demand high dynamic load balancers that modify the breakdown as computation progresses. There have been numerous strategies developed for static and dynamic load balancing, such as recursive bisection, space filling partitioning, and graph partitioning methods. These techniques provide useful splitting for a wide range of applications, implying that the load balancing problem has been solved. Crash, particulate, and adaptive finite element simulations all use RB and SFC methods. Because of highly quality and serial concurrent graph partitioners, graph separation is useful in conventional responsive and continuous finite difference simulations. As an important first step to create application that enables techniques to be validated and reused, properly crafted library functions that assist many applications benefit application developers while also serving test beds for analytical research. Furthermore, partitioning algorithms must be sensitive to current heterogeneous system architectures, adapting work assignments in relation to processing memory and communication resources. Although this new strategy has very low latency, it comes with other drawbacks. Because only one methodology was applied, the programmers cannot compare the program's potency for application to other strategies. And because it is too closely tied to the original applicant's data structures, they eventually result in execution that is not compatible with other applications. These computer science issues are effectively addressed by software toolkits. Toolkits are libraries that provide professional configuration of interfunctional algorithms. To aid applications, they frequently include commonly used additional services and primary purpose. Toolkits are intended to be used with a wide range of applications and data structures. As their use expands, they gain from more detailed evaluation. Of course, using toolkits incurs some overhead for applications, but this load can be kept to a minimum with careful design. While software developers must rely on toolkit developers, open source software toolkits allow for careful examination of implementation. Now we move on to the workload allocation in parallel systems. The assignment of workload allocation to logical or physical assets is referred to mainly resource allocation, which simply expresses a different viewpoint on the allocation problem. Special allocation problems such as transfer of funds and query allocation or CPU and RAM allocation can be able to determine the workflow or resource type. Load balancing is the process of allocating workload requests among multiple processing nodes in distributed systems. Even in the central case, heterogeneous database workloads containing OLTP transactions of various types, as well as critical decision support queries pose unique resource management challenges. Here we see the image of workload allocation that is done in parallel systems. The request first processes through the workload allocation, then through the program allocation, followed by the data allocation, and then it moves to the common database that is shared by multiple nodes at the same time. Depending on the degree of parallelism, load balancing can be used for different workload granularities. At the best stage, we have the cross and interquery parallelism with individual transfers and queries running concurrently. The corresponding task scheduling is concerned with delivering transactions and requests among processing nodes, whereas interquery parallelism necessitates additional types of task scheduling for allocating subqueries to nodes. In this context, several types of intra-query parallelism can be distinguished, including inter-operator and intra-operator. Pipeline parallelism is also commonly used for inter-operator parallelism. This allows for execution of many operators within a query to be overlapping. While both data and pipeline concurrency are required, transmission parallelism is generally regarded as less effective in order to decrease query reaction times. Task scheduling is difficult to attain for transmission parallelism due to prioritization correlations between drivers and because individual tech assets' execution times vary greatly. Moreover, the magnitude of provisional results is difficult to predict. At runtime, careful flow is required to ensure that the information produced by producer operators is processed quickly already by the buyer operators. Otherwise, the input data from the consumers would have to be stored in temporary files, introducing a potentially large amount of disk I/O. So now we conclude the paper by stating that dynamic load balancing is required for the effective use of parallel database systems with many processing elements. Intra-query parallelism must be supported effectively in multi-user mode, that is, in conjunction with cross and inter-transaction parallelism. The main dynamic control decisions are determining the extent of intra-query parallelism as well as choosing the processing power for executing subqueries. Task scheduling should be backed by versatile transaction routing for initially query and transaction assignment. While progress has been achieved in dynamic load balancing for concurrent and unstructured applications, research is still ongoing to address these issues that arise as a result of application and architecture requirements. New algorithms are being enhanced to meet the unique requirements of complex applications. New hypergraph models are being developed to better represent highly related, non-symmetric, and shaped systems encountered in wave functions, circuit simulations, and mathematical programming. New algorithms are also being enhanced to meet the requirements of complex applications. Thank you.